NP hardness we are done, but I promised degree 3. None of you actually pointed it out, right? So the degree is not 3 here, right? Degree is not constant here, degree is large, right? But to make it constant, here's a standard trick for such kind of reductions. Okay, the trick is what you can do. So look at this P1. So look at this P1 tilde, P2 tilde, doesn't matter. We will do the same thing from the both the sides. You can look at P1, P1, P21. So we try instead. What did we do earlier? We connected everything from same P1, right? But instead of that, you build a tree structure there, right? Connect two vertices together, right? The number of vertices reduced to half. Whatever you had U1 copies, right? Connect two of them to one vertex. It reduced to half. Then again take two pairs, connect them, reduce to half, and so on and so forth, right? So you will have log of Vi sized tree additionally. Okay, and now you can give the preferences accordingly. You can do it from both the sides. Okay, and you can do the same thing for Qijs. Okay, so here you can notice for Q even whatever it was there earlier, we added everything with same Q1 too, right? Now I have for even prime I have one Qij, right? For even tilde even hat I have another Qij, correct? Then for both of them we are doing this thing. Okay, such kind of tree structure you can just build. Okay, this is a standard trick to decrease the degree. Okay. Now, so there were three types of high degree vertices, right? One was Pis, Pi tildes, Qijs, Qij tildes, and this degree 3 vertices, right? So for that what we can do, notice here, instead of 1 degree 3, we have stretched that path as well, right? So basically one vertex will be incident to one edge vertex, right? We will have another vertex copy to connect with other edge vertex, and so on and so forth. Okay, so this is how we decrease the degree to 3, right? Because now U3 is connected to two vertices in the same vertex class and one edge vertex. Okay, there was one E1. E1 also had degree 4, right? For that also you will do the same thing. Earlier we had just E1, E2, right? Now I have 4 length path, 3 length path, E1, E2, E3, E4, right? E1 you connect with one endpoint, E3 you connect with other endpoint. Okay, so this is how you can decrease the degree, okay, and fix the preferences so that whatever was a fixed edge earlier still remain fixed edge. Okay, this is just one edge and rest of the effect will trigger, right? Still we would like that corresponding to every vertex class, right, endpoints are unsaturated, right, so that we have augmenting paths there. Okay, okay. That's all about NP hardness. Any questions? Please ask now. We'll switch to degrees algorithms now. Okay, so we saw two things, right? When number of blocking edges is constant, we can do it in polynomial time, right? But when it is not constant, right, we have NP hardness, right? Here you can see that number of blocking edges is quite large. Okay. What are the next questions? For degree 3 it is NP hard, but what happens with degree 2? One question. Next question. Can we hope for such an algorithm? Here ft is any arbitrary function, right, computable function, but it only depends on t. Okay, this function has no dependency on your input size. Okay, so ft n of order 1. Okay, can we hope such an algorithm which has exponential dependency, which may have exponential dependency on t, but only polynomial time dependency on your graph size, input size. Okay, okay. Next question. Can we hope for an algorithm that can have exponential dependency only on k, number of blocking edges, but only polynomial dependency on input size? Okay, so here also one thing. This T is not the size of the matching. This T is the increase in the matching, size of the matching. Okay. Now, can we have with the combined values K and T? Can we have such algorithm? Okay. So, these are the kind of questions we can ask. Okay. So, this is basically mu minus. Okay. Mu minus, so this is so this is basically f of mu. Mu is the size of stable, mu is a stable matching, sorry, this is T minus mu. Okay. Okay. So, we are asking that you are allowed to have exponential dependency on this value T minus mu, whatever it is. Okay. For example, in the previous case, this value will be K tilde plus K tilde choose 2. Okay. So, you are allowed to have exponential dependency on this, but you will not, should not have exponential dependency on n. Okay. That you can have only polynomial dependency. Okay. So, same is with other cases, right. So, answer is this is pure, this when degree is constant we can do in polynomial time, we can come up with a dynamic programming algorithm, and the reason is simple, because when degree is at most 2, right, it is basically the collection of paths and cycles, right. When you have collection of paths and cycles, really you do not have many choices, right. One of the edge is part of matching, one of the edge is part of blocking edges, so we can take these decisions in your DP, right. Okay, answer to all the other questions is no. Okay, and this is just due to the reduction that we just saw. Okay, because for click also, for click we can't hope for f of K tilde with only this . So, okay. So, here I am not using technical language, undesirable happens, because these are the complexity classes which I am not sure you know, FPT, W1, okay. So, like P and P, there are other complexity classes, so unless something fails, we cannot hope for such algorithm, okay. Whenever we have such hardness, there is some conjecture, okay. Okay. Let me not use it. Clear all my annotations. Okay. So let me. So now we saw a lot of hopeless things, right? We cannot design such algorithm, that algorithm, right? But ultimately we are interested in designing algorithms, right? We want to solve problems, okay? So let us look at what more can we do, okay? Let us say this is a stable matching, some stable matching, fix it. There are a lot of other matchings around it, okay. So, and there are a lot of matchings which are actually our solution around it, right. It's just we are not able to find it efficiently, okay. But what if we decrease our search space, okay. Now my question is not to find any stable matching which is large enough with at most k blocking edges, but I am also saying that that particular solution should also be close to mu, okay. So I decreased my search space. Now can I hope for some good algorithms, okay. So when I say that close to, we need to quantify this, right. What do we mean by close, okay. So two matching distance is symmetric bit difference between two matches, okay. Okay. Now the question is this, we want to find a, forget about this table, we want to find a matching of size at least t with at most k blocking edges that is close to a stable matching mu, okay. And close notion is the symmetric difference between your solution matching and mu is at most q, okay. So this is called a setting of local search, okay, because we are not finding anywhere, we are just finding in the vicinity of a stable matching, right. So this is local, okay. Okay, so now this is our question, okay. So does there exist a matching eta whose size is at least t, the number of blocking edges is at most k, and symmetric difference is at most something q, okay. Okay. Again, unfortunately this question is also NP-hard, and if you notice in our previous reduction when we did not decrease the degree, right, what was the symmetric difference? Symmetric difference was also k tilde plus k tilde choose 2, okay. So that means with respect to q also I cannot hope for an algorithm that runs in f of q with just polynomial dependency on n, right. Even that is not possible, okay. This is the same NP hardness tells us this as well, right. Okay. Now k plus t plus q, in our previous reduction all these values are function of k tilde, so I cannot hope for this algorithm. I am increasing my parameter little bit like slowly, but still I am not getting any any algorithm basically, okay. We cannot hope for k plus d because of my degree 3 reduction. There we had just k tilde plus k tilde choose 2 blocking edges, right. Okay. T plus d again because of the same reason we cannot hope, okay. But when we try to decrease the degree, we have long augmenting paths, right, because we added lot of new edges, right, and when there is an augmenting path all of them are basically contributing to your symmetric difference, right, okay. So in that particular reduction when d is constant, q is large, that is no longer function of k tilde, right. So that reduction does not tell me that you cannot have q plus d, and actually we can have, okay. This algorithm we will see which will have exponential dependency on q and d with just polynomial dependency on this, okay. Okay, now let us make some observations first, okay. Let us say whatever is your instance, but these zigzag edges are in your stable matching, okay. By the way, for local search I need to fix my stable matching, right, around which we are looking for the solution, okay. So let us say these zigzag edges are in mu, okay, and let us assume there is some solution, okay, and let us try to visualize that, okay. We are not saying that we have this solution, assume hypothetical solution, okay. How does it look like? Now if I look at this, okay, let us say eta is my hypothetical solution and these blue edges plus black zigzag edges is my eta, okay. So this zigzag edges basically it means that, see, if I have these two edges, blue edges in my solution, right, clearly I do not have this zigzag blue edge in my eta, correct? It's matching, right? Okay. And these solid edges are in eta but not in blue, okay? Okay. And these black zigzag edges are in both the matches, okay? So essentially what do I need to compute if I want to compute eta? Tell me. Do I really need the whole eta? Exactly. I need to know the symmetric difference, right? If I know the symmetric difference, I can compute eta, okay? Okay. So goal is now to know these blue edges which are symmetric difference edges. So far so good? Okay. So what we will use here, we will say that, again this is all under the assumption, I am going to give you a randomized algorithm now, okay. So we want to highlight the endpoints of edges that are in symmetric difference, okay. Okay. So for that what we do, and we also want to highlight the neighbors of, okay. So we want to highlight the endpoints of edges in symmetric difference, okay. So I do not know if this color is visible, but these green vertices are my symmetric difference vertices, okay. Okay. And I also, basically what do I want to do? I want to separate my solution from rest of the graph, okay. So to do that, what we do, we highlight the vertices which are part of my solution and their neighbors should be from different color, okay. So we highlight their neighbors using, let us say, some blue color, okay. So for example, if you notice U1 W1, U2 W2, U3 W3, U4 W4, all these are symmetric difference vertices, right? And what are their neighbors? U5 and W5, okay. So I color U5 and W5 using blue color, okay. These colors are not visible even to me, okay. So now this is our goal that we want to highlight, right? But what does that mean mathematically, okay? So because we do not know the symmetric difference, right? That is what we want to achieve, right? So what we do in such cases, we randomly color vertices, let us say using green and blue color, okay? And we will see that with what probability, right, I will achieve that we want to achieve, okay? So my operation, whatever I said that, oh, this is my symmetric difference, how does it look like, highlight this, that, okay, these all is part of understanding, intuition. But the step is just this, you randomly color vertices using green and blue color, okay? Okay. And this is uniformly at random, okay. Now what do we want? We want that, what should coloring do? That it should color the symmetric difference vertices using green color. It should color its neighborhood using blue color, okay? Okay. And this is what we mean by good coloring. This is what we will call good coloring, okay? Okay. So this we will do uniformly at random. These are just two colors, so everything happens with probability at least half, okay? So again, what is the probability that f is good? So we need to understand that with what probability all these desired things will happen, okay. So what is the probability that mu symmetric difference eta is green vertices? How many vertices are there? 2q, correct? Because mu symmetric difference eta can be at most q, right? So what vertices in this set is at most 2q, right? So this will happen with probability this much, right? Neighborhood, let us say d is my degree. So this all will happen, right? Because every vertex can have just d degree, right? D is the, let us say, maximum degree. So this is the probability of happening this blue things, okay? Okay. So now the probability that f is good is at least this much, Okay, do you all agree with this? So what did we do so far? We just highlighted the vertices that are in mu symmetric difference eta. We still don't know the edges. Okay, there might be there are a lot of edges incident to these, right? Okay, and fine, we'll come to that. Okay, now let us look at the graph induced on these green vertices. Okay, we know that if something like if f is a good function, right, then with respect to this good function, this mu symmetric difference eta is part of VG green, correct? Because this has been colored using green color. Okay. Okay. Now let us say C is a component in this. Okay. U is in this component. U is saturated in mu, but mu U is not in C. What can I say? Right? So there is one more thing, that U is saturated in mu, but U is not saturated in eta, let us say. Okay. So if U is saturated in mu, but U is not saturated in eta, then I know that it cannot be part of symmetric difference. Sorry. So U is in C, okay. U is saturated in mu, right, but mu U is not in C, right. What does it mean? If it changes the partner, then this vertex will be part of symmetric difference, right, but its mu partner is not there, right, no matter whether it was matched or unmatched. But if its partner is not in C, it means whatever its partner was in mu, the same partner is in eta, right, because it is not in the component, right. Okay. So I know that this component cannot be part of my mu symmetric difference eta. Okay, because it did not change the partner, right. U is in C, but it did not change the partner, right, because its partner is not in C, right. Then why U is in C? Okay. Okay. So this is the crucial point. Okay. So now before going forward, we need to remember few points. Okay. These are the crucial points whatever we did so far. Definition of good coloring function. Okay, who will tell me the definition of good coloring function? Not you. Definition of good coloring function. A function is good if it does what we want to do. What do we want to do? I can't hear. No two vertices of same color. Why? Why? We are not solving coloring problem here, right? What did we want to achieve? We want to say that mu symmetric difference eta vertices should be green colored. So of course there will be edges whose endpoint will be of same color, right? Because if an edge belongs to mu symmetric difference eta, its endpoints are green, right? And the neighborhood is blue, right? Outside neighborhood. Okay? So this is what we want to achieve. We have not deleted anything from the graph. This you need to remember. I focused on the components, but we have not deleted anything. Okay? Green, blue, everything is there. All the vertices, all the edges are there. I just colored, give some colors to the vertices. That's all. Okay? One of the endpoint of blocking edges is in symmetric difference. Tell me why? Because if it is not, then mu was also not a stable matching. Okay? Yes or no? something is UV is, let's say, a blocking edge, right? Okay, and let us say partner of U is in mu and eta is same, partner of V is also same in mu and eta, right? What does it tell me? This blocking edge is also in mu, right? Correct? Yes or no? Tell me, otherwise we can look at example quickly. Otherwise I will take your lunch time. You have tired out, now you are speaking. Okay. Let us say this is your blocking edge, okay. Blocking edge it is, okay. So let us look at their matched partners, okay. You are saying that it's none of this belong to symmetric difference, right? It means that V is matched with mu's partner is same as mu V, and this is also mu U, correct? Now if it is a blocking edge, what does it mean? U prefers V more than mu U, correct? And V prefers U more than mu V. So UV is a blocking edge in mu, but mu is a stable matching. So it cannot happen. Okay. One more assumption which we, so it is safe to assume that, let us say eta is a solution, okay, such that in every component, okay, if you look at the symmetric difference edges, then eta edges are more than mu, okay, and this is a safe assumption. We can say that, okay, let us say you have a solution where this does not happen, then you actually do not need to augment there. Do not augment because it is anyway not increasing the size, and because of our coloring you can also show that because of that it will not happen that it was required for some blocking edges, that will also not happen, okay. So this is our safe assumption and we need it, okay, for our algorithm. Okay. Now GF is a colored instance where F is a good coloring function, okay. So now I am saying that look at the colored instance where I know F, like it is nicely colored, okay. You all are with me? Okay. Now what happens, indeed I know the vertex set now, right, but I do not know what all edges are part of my matching, symmetric difference, what are blocking edges, right. So now within this set we will try to highlight symmetric difference edges, okay. So highlight symmetric difference edges. Now randomly colored edges within this green set using blue and red as we have already done it, okay. All the other edges you do brown color, we do not care. We just need coloring because we are not deleting anything and it is a colored instance, okay. So now what we want, okay, because again our function is just this, we do random coloring, okay. Now we need to understand what is the probability of good coloring and what is good coloring for us, okay. So we want that every edge in mu symmetric difference eta is colored blue. We want that every edge which is not in mu symmetric difference eta but its endpoints are in mu symmetric difference eta, then it is colored red, okay. For example, this U2W3, okay. I am telling you that it is not a symmetric difference edge, right, but its endpoints are in symmetric difference, so such edges should be red, okay. Okay. And every edges which is outside this green components is brown, okay. This is the definition of my good edge coloring, okay. Now I will assume that my GF is a good colored instance and my G is also good coloring, okay. Now what is the probability of that G is a good edge coloring, okay. So I think this is simple coloring like probability computation, you can do it. Because Q is the number of symmetric difference edges, it will happen with this probability, okay. Now let us assume we have colored the graph nicely. F is good, G is good, everything is good. So because it is good, we know that V mu symmetric difference theta is subset of green components and mu symmetric difference theta is colored blue. Okay. Now you recall that we did this in quiz, right? This was the purpose. Okay. So I hope you all understand the reason. If you not, then tell me. You understand, right? By mu symmetric difference theta, form vertex disjoint maximal mu alternating paths and cycles. All of you understand it? Sure? All of you are not saying yes. Okay. Let us look at the components. Useful components are components that contain. So see, we did random coloring, right? We know our desired things happens with some probability, right? But lot of other color things may get the same colors, right? So how to understand what all components are there which will really give my solution, right? See, my size of solution is small, so I could bound that probability, but the non-solution things are large, right? So I cannot do I can do, but if I do that will not give me the desired running time. Probability of success is going to be very less. Okay. So now I need to understand what are the components that are good for me. Okay. Let us understand this. Look at this component. Okay. So this, let's say these solid edges are same as earlier. These are eta edges and these dotted edges are mu edges. Okay. Tell me, can it be my solution? Can it give to just recall what do we want to do in our good coloring, right? What do we want to achieve? Can it be my solution? If I augment on this, right, is it my solution? Let us say component just look like this. No, because this green vertex is not part of symmetric difference. Then what is it doing in my component? See, essentially what we want to do, we have components, right? And I know that symmetric difference edges give me disjoint alternating paths and cycles, right? So so my component should have such kind of, that if you look at the blue edges, what is the purpose of blue edges? Blue edges are my symmetric difference edges, right? So if you look at the symmetric difference edges, that should give me mu alternating paths and cycles. Okay, this is one thing. Indeed, this blue edges is give me alternating path, fine, this is also another drawback, but what is our problem, what do we want in my component? I want to augment, right, and I said that my symmetric difference endpoints are colored green, okay. So this is a vertex which is colored green, but it is not part of my symmetric difference because the edge is red. G is also good coloring, right, but this edge is red, this is not blue. So this green vertex is not part of my symmetric difference. So this is not the component which is going to give me solution. You get it? What happened, Sanjay? Please give me mic. Correct. That's right. Exactly. So this is exactly what happens in randomized algorithms, right? That useless things also get our color, right? Useless things are also getting my color, and that is why what we are trying to prove, right? We are trying to see what all components are useless for me. Okay. So if it is part of my symmetric difference eta, then it would, right, then it should get the color green, right. But if this component, let me complete. So if this component is going to give me the symmetric difference edges, right, then its endpoints are green, okay. So what will I do in future, right, that if you look at the component, I will augment on it. Okay. This green vertex is extra here, right? This is not part of my symmetric difference, right? But if I look at my solution, right, then my if you look at the solution, right, if you just look at your blue edges, right, that will lead to a component. So those components are here because I have done my good coloring, right? So those components are here, which we need to search. Getting?
Is it possible that such a path is there using the same component does not consist of these?
Which are?
There are many other vertices inside this component. Is it possible that?
No, endpoint should be blue, right? Symmetric difference is green, right? And the outside neighborhood should be blue, right? So it is not a useful component, right? Because when we say highlight, meaning my solution should be highlighted and I am trying to separate it from its neighborhood. Okay? Okay. Yeah, that's the reason we already completed it. Now let us look at this. Is it a useful component? Why? Correct. So what she is saying that mu edges and eta edges are same here, right? And what is our assumption? That we have a solution where every component will have more eta edges, correct? So this cannot give us solution again. Okay. Okay. What about this? Yes. What about this? Just try to use the properties. If you look at blue edges, right, is it giving me symmetric difference? No. Right? Because look at that blue edge, that is not a symmetric difference edge. This one, the top one, right, just one edge. Right? Where is its dotted part? Right? So this is also not a useful component for me. Okay? Just get rid of those components. All these components. Okay? Now, these are the definitions of my useful components. Okay? So every green vertex should be incident on at least one blue edge. Blue edge form vertex disjoint maximal mu alternating paths in cycles. Non-new edges are more than blue edges in component. Okay, component is anyway there. Okay, and I will assume that GFG is a good colored instance. Okay. Okay. Now goal is to choose the components for alternating paths and cycles appropriately that satisfies constraints. Okay. So now when I know that in my useful component eta edges are more than mu edges. It is also giving me symmetric difference. So what are the other constraints? Because eta edges are more, size wise they are good. We know at least they will be increased by 1. Okay. It may not be very useful to augment on that, but at least I know that augmentation on that particular component is going to give me increase, right. But there are constraints of symmetric difference as well as blocking edges, correct? The first thing we will do, we will just keep the useful components. Okay. Now let us look at this. There are green, right? We just keep the useful components, but there are some blue vertices. We do have those vertices, right? Okay. These are, let us say, some good components. Okay. Where are my blocking edges? Let us understand that. What about the symmetric difference edges? Those are within component, right? So when I am augmenting on a component, I know what is going to be the increase in the size. I know what is going to be the symmetric difference, right? But what are the blocking edges? Okay, blocking edge can be within the component, right? You augment and you get a blocking edge. Where are the other blocking edges? Can we have any other blocking edge? Across the components we know there is no edge, right? Because these are components, right? There are no edges. Where are the other edges? Where are the other edges? Come on, where are the other edges? Huh? Where are the other edges? Correct. We don't have. Why don't we have? Of course we can have, right? We can have such edges. Why can't we have? Right? This does not, like, we cannot have between two components, that's obvious, right? Why not these edges? Of course we have, we may have, right? We have not deleted again. Okay? Okay. But can this edge contribute to my blocking edge? What is the property of that blue edge? Blue vertex. This blue, yes? Correct. Why?
We are not going to change their partners in our new matching.
Correct.
So only the vertices which are part of our component, their partners are going to change.
Correct.
So we need not consider the edges that goes out.
No. But see, these edges can contribute to blocking edges, right?
Yes.
That is why we need to consider them. How can they convert? What do I know about these blue vertices? She is very right. She is saying that for these blue vertices, mu partner is same. Mu partner and eta partner is same. Okay, because these are not part of symmetric difference, right? But that doesn't mean that there cannot be a blocking edge incident to it, right? For blocking edge, we just said that one of the endpoints should be part of symmetric difference. Okay, so these brown edges, right, can be part of blocking edges. Okay, so looking at, if I decide to augment on a what you call component, of course I immediately have count of increase that we are going to get in the size of matching. We also know the value of symmetric difference, right? But given the fact that these blue vertices are not changing the partner, right, can we compute the blocking edges incident to this component if we augment? We can, right? Because I know what is the new matching here if I augment, right? And the other blocking edges are this, and I know these blocking edges. These are all under the assumption that our coloring is good. Okay? Okay. Does it look similar to some problem now? Okay, fine, let's see. It reduced to two-dimensional knapsack problem. Okay, let us see what is this problem. How many of you know about just knapsack problem? Knapsack problem, all of you know. Okay, if you are reading just okay. So what is two-dimensional knapsack? As the name suggests, you have two dimensions. Okay, so you have a set of tuples here. Okay, and non-negative integers C1, C2, P, right? And we want to choose some sets or tuples such that summation of first values is at most C1, summation of second values is at most C2, and summation of third values is at least P. Okay, like in one dimensional knapsack you have budget constraint, profit constraint, right? So you have, in some sense, you have two budget constraints here. Okay, that's the difference. Okay. So what is the reduction? Now for every useful component, right, if I decide to, see, if I augment on it, I know it is going to give me the increase in the size. Okay. So whatever components now I have, right, I know every component is going to give me the size, right. I just need to fit in the values, right. I cannot pick any components, right, because of our size constraints, right. So that is what we need to pick carefully, right, and that is what we will achieve using this knapsack. Now you see the relation, right. So for every useful component we will have a tuple qi bi ti, let us say, give some name. Okay, Qi is the number of blue edges in Ci. What is it giving us? Basically it is giving us symmetric difference, right? If I augment on Ci, right, then Qi captures the symmetric difference value, right? Correct? What is Ti? Ti was the increase, right? So you basically now you need to look at in your component, you need to look at non-mu edges. That is non-mu edges, difference between non-mu edges and mu edges, right? That is the increase, right? That is why we have done Qi minus twice of mu edges in Ci, right? Okay. Now Bi will capture our number of blocking edges. Okay. So what is Bi? We have already discussed it, how to compute the blocking edges incident to vertices in a component, right? So if you look at this vertex, blue vertex could be matched in mu, could be unmatched in mu. We don't know, right? But I know this information because I know mu, right? Look, eta we are just using for analysis, we don't know eta, okay? So this vertex, whatever it is, matched, unmatched, but I know it, okay? Okay. So now let us compute a matching zeta I. So zeta I is basically non-mu blue edges in Ci, right? And zeta I contains mu edges whose endpoints are blue, meaning outside these components, okay? Now look at the graph induced by all these vertices, basically the vertices in Ci, all the vertices and this zeta I vertices, right? Their neighborhood, because Ci, like their neighborhood can also contribute to blocking edges, right? Okay. So basically Bi is the number of blocking edges with respect to zeta I in this graph Gi. Do you all agree? We all already discussed it. Okay? Is it clear or not? Yes? So what is zeta I? Zeta I is telling, so Ci is basically the potential component where I can augment, right? Now what is zeta I? The matching obtained by augmentation in Ci plus the edges which are part of mu and eta both, which are not part of my symmetric difference, right? Right? Whatever is the other matching, okay, eta, my blocking edges are not incident to that part, right? Right? If the one of the endpoint in blocking edges in C1, the other part is not anywhere else, C2, C3, it is not there, there are no such edges, okay. So is the computation of blocking edges clear? Okay, that is all. So we reduce the problem to two-dimensional knapsack problem, okay. But we also need to talk about constraints C1, C2 and P, okay. Okay. What is C1? Q. One constraint is K, number of blocking edges, and the other constraint is T minus mu, right, for how much you want to increase, okay. Okay. So now if you notice, we have reduced to solving two-dimensional knapsack problem, okay. And the values here, what do we know about knapsack? Forget about two-dimensional knapsack. What do we know about knapsack? Is it polynomial time solvable in some cases? Do you know any algorithm for knapsack? NP hard, but there is a pseudo polynomial time algorithm, right, dynamic programming based, right. So it means that when the values are small, right, then the algorithm is solvable in polynomial time, right. In this two-dimensional knapsack, right, you can see that all values are indeed small. Small by small, I do not mean constant, it is polynomial in input size, right, right. Okay. So this can be solved in polynomial time, two-dimensional knapsack also using the similarity, it just you need two dimensions now, that is all, okay. Okay. So running time is polynomial, but this is the success probability, right. Probability of success of f multiplied by success probability of g function. vertex function and vertex coloring and edge coloring function, right? Okay. So which is not good actually, right? 1 by 2 to the power 3q plus 6qt. Okay. So to increase the probability, to boost the probability, the standard trick is run it multiple times, multiple trials, right? Okay. So if I do it, if I repeat it, let's say 2 to the power 3q plus 6qt times, right? The probability, so this is the 1 minus, this inner factor will give you what is the probability that it always fails, right? What do you want? You just want to compute the probability that it succeeds in at least one of the trials, right? What is the probability that it always fails, right? That is it 1 minus 1 by 2 to the power 3q plus 6qd to the power 2 to the power 3q plus 6qt. This is the probability that it always fails. Then succeed at least once, just subtract it from 1. Okay. Does it look good? Yes, why? Who said yes? You said yes? Why? Because you know that it does. Why? Like this is such a very odd function, right?
Yes.
No?
Yes.
But it tends to this. Okay. And E, you know, it's between 2 and 3. So now if you repeat it, then the success probability really increases. It's more than half. Okay. You repeat more, you get success probability increases. Okay. So this is true even always with the randomized algorithm, that you repeat it multiple times, right? So running time increase, success probability also increase. Okay. Now if you notice, the running time is because of this repetition, right? And in the running time you have q and d as exponential factor, right? There is of course polynomial factor as well, which I ignored. So that is why we achieve this q plus f of q plus d with polynomial dependency algorithm. Okay. Now there are some actually hidden things which I did not discuss, that why do we really need two-step of coloring, right? Why do we really need to first color vertices then edges? Why not directly color the edges and try to highlight the symmetric difference edges? Okay. Any idea? Any guesses? So the reason was actually simple. Okay. We do not want that blocking edges goes between the components. Okay. That is why we first try to highlight the vertices. So now the blocking edges are either within the components or between those vertices which are not changing partner. And this information I have. Okay. What is the issue if the blocking edge goes across the component? What is the issue if the blocking edges goes across the component? No, still my definition of good components could be that, right, I will only augment if the mu eta edges are more, non-mu edges are more, right. But the issue is you want to choose the components, right. How will you compute the blocking edges? I told you that, oh well, this is my number of blocking edges, this is my ki, right. How will you do it if your blocking edges are going across? You don't know which components are you picking, right. You want to choose the components. So number of blocking edges will depend on what did you pick, right. If you pick C1 earlier, then the number of blocking edges in future are going to be different. If you pick something else, the number of blocking edges is going to be different, right. So how do I compute this value? Okay, there might be solution, but this is not that easy to do. Okay, then we cannot immediately reduce it to two-dimensional abstract. Okay, that is why we try to localize this property, right? So that just by looking at the component, if I want to augment it, no matter what happens in future, I can tell you this is the contribution for the blocking edge. This is the contribution for increase in size. This is the contribution for symmetric difference. Okay. So just by looking at the component, if you try to augment, we know what is going to happen in future. Okay. This is why we first try to highlight the vertices, endpoints, and then the edges. Okay, any questions? No? Okay, good. So the next lecture is, and our last lecture is at 2 p.m. Please just don't just go to the city, go after 3 p.m. okay.